Whether my screen is visible?
Yes, sir.
Okay. Okay. Thank you. So this is before I start another concept on this regarding the learning process. I want to tell you that what's the reason or the rationale behind not using a linear function or identity function as a activation function, because we said that activation function is always a linear function, sorry, no linear function. So what's the reason behind that? So just a minute, this is so for that to understand, let's take a simple architecture, and that will also, so this whatever I'm going to talk about, it will also formalize or form a base for the deep learning. Like what I'm trying to say is that uh, it will basically give an idea how the deep learning architecture are framed and analyzed. So let me see a very simple two-layer architecture. Two-layer architecture, very simple. Let me say three input two-layer architecture. Let me call it as x1, x2, x3. Let me take some 4 neuron here. So 1, 2, 3, 4. Assume that output is only 1. Let's say it's just arbitrary architecture. I just want to give the idea why we are looking for this no linear activation function. If we do activation function linear, what will happen? So normally such kind of questions are not answered directly in most of the book. They say that it's linear, but why? So they say it is non-linear, but reason won't be given most of the time. They are probably way to work out, they assume so. So I'm saying it's a fully connected network. Okay. And let me call as the outcome of this is say A1, A2, A3, A4. A stands for activation output. You can see that. Likewise, and this let me call overall function, say h of x, whatever it may be, or y of x, you can say that. Ultimately, it is working. Now you know that there is a this kind of weights will be there here because it's the first neuron getting input from the first input. So normally as per our notation, it should be 1, 1. And the first neuron getting input from the second one. So as per the notation 1, 2. And likewise, this should be 1, 3 as well. Likewise, right? So this entire weights, which is part of this section, that is from the input layer to the hidden layer. So this you know that now you know very well. This is the input layer, this is hidden layer, and this is the output layer. So the set of weights between the input layer and the hidden layer, let me call this as a capital W and superscript in square bracket 1. Just to get an indication that it belongs to the first one. And here this entire weights of this one, let me call this as a 2. So you know the entire story. We'll be writing like this, W11 x1 plus W12 x2 etc. plus of course the bias of this, bias of this, bias of this, and pass through the activation function. And based on that particular this one we can write a matrix for this. So this is what is given here, right? Now let's say that I'm using a simple uh, uh, let's say activation function which we are not doing anything, and let me denote it by phi, whatever it may be. So whatever goes here, the phi, and this will be the activation function, right? So here when I say one particular thing, like I'm assuming that my x is of dimension D, whatever it may be. X is of dimension D. So what I can do about this, and let's say, for example, here only written 4. Let me say these are some m number of units. Let's say it is some m number of units. So in that case, if I want to write all these A's in general, A's in general, can you tell me the A1? Any one of you, what should I write here? A. A1 is nothing but the outcome of this particular, where is that? This neuron. Can anyone of you tell me what should I write or what I can write here? All the background stuff.
So the weight of that, so W11 into X1 plus the bias. So
only that one?
no, so it will include X2 and X3 as well, multiplied by.
Yes, sir.
Yes, yes.
W1 and W1.
Yes. So we have to put everything. So W12X2 plus W13X3 plus bias of this particular neuron. Perfect. Now if I'm writing like this, is it possible for me to generalize this? Means, can I write a generic expression so that I can write it in general? So do you mind if I write AJ equal to, and not only this, phi has to be there. Am I right? Because this entire thing goes in the activation function. This is called activation. So correct? Okay. So I can write now phi here summation I equal to 1 to D. D means how many inputs are there, right? And I'll write here that Wji, right? Xi. Am I right? Is it okay?
Yes, sir.
Okay. Now, to make a little more formal, we can say this particular process, and we can say that this is the activation function corresponding to the first layer. We have mentioned one superscript here, and we say weight one superscript here. But anyway, don't want to confuse now. For the timing, only this. This entire thing as a vector, do you mind if I write A equal to A1, A2, say AM, T? Because I said that imagine that there are m number of inputs. What weight may be? It has to be that one. So if that is the case, if that is the case, what I can write about here, right? And this is WT is there, WT. And of course, you know that A is basically a vector of dimensionality m. M number of components are there, A1, A2, A3 till An, right? Now, so let's move little further. And if you see here, Hx, can you tell me what should be the Hx? What should I write about the Hx? Any idea? Any one of you?
So A1 into weight of A1 and A2 into plus A2 into the weight of A2.
Correct. So you are on the line. So let me just call it, just label it as some O, simply O, just an idea. So I can write this h of x equal to, I can write some phi, whatever it may be, and then we'll write WO1, WO1 A1 plus WO2 A2 plus WO3 A3, say plus WOM AM, and of course corresponding to the bias for this W. Is that okay? Is that okay?
Yes, sir.
Yes, sir.
Now I want to generalize one thing. I want to say something very specific here. This I'm talking in terms when it's only two-layer network, chances are there you can have it something like this, no issue. That there is an activation function here also. But suppose you are using a ReLU function. So in the most of the deep learning network, ReLU function will be used as an activation function anywhere before the output layer. But in the output layer, we write the linear function only. The reason or the rationale behind is that you know that ReLU function is defined basically. ReLU is defined as nothing but max of 0 and x. Ultimately, what you mean to say that it will not allow this negative value to be there, right? If negative is there, it will make 0 and it is something like this, always positive. But in the output layer, you want if the negative is there, so let it be there so that interpretation can happen, right? That's why, because this question can be asked, why in the deep learning or deeper network, the output layer does not use any other activation function other than the linear function. But anyway, for the time being, only this. Now, suppose your activation function at the output is linear, what will be the hx? How should I write hx? What should be written as a? When you say linear, suppose if phi is a activation function which is linear, so whatever x is there, same x will appear. This is a linear function, right? You do something like this. What is here? It is appearing that way, right? So same thing. So ultimately, what I'm saying that I can write A1 plus WO2, A2, etc. plus BO. Now let me write a more formal. Forget about all these things and say this is layer 1, this is layer 2, and which I said I'm denoting layer 2 with a superscript in square brackets 2. So do you mind if I write this entire thing in a more formal setting as a vector or representation? So can I write so? The weight corresponding to the second layer multiplied by the input from the penultimate layer, from the previous layer, that is A in this case, that is A plus B2. B2 means the bias of the current layer. When I say bias, here there is only one neuron. But imagine the situation there are multiple neurons. So this, let me see what this matrix is all about. So let me open it up a little bit. And I can say that here I can write this one, I can write it across for the timing. I can say if I'm saying only W1, say, let's say. So it will be nothing but W1 transpose and the first component, W2, of course, transpose second component. Likewise, sorry, this will be one only. Say M component. So this is entire W1 matrix, that is the weight matrix corresponding to first layer. And when you say W1 and transpose, so remember that it is not a scalar, it's a vector which is written in this particular fashion. If that is the case and we have this, so definitely its dimensionality will be, in this case you can make out M cross T. You can check it out. Now activation potential Z, etc. we have just found it out. And I told you this this entire, suppose here whatever goes which you have written here, this entire part which I am calling as the activation potential, if I want to denote it as say some Z, so do you mind if I write X plus B1? See the diagram and tell me whether it is right or wrong. If you see this diagram, question is, here A is nothing but the output of the activation function corresponding to this particular layer. But before that, something will go inside, isn't it? And that is the activation potential. So if I'm denoting activation potential as a Z, do you mind if I'm writing it as a vector W1 X? When I say X, is not the only one. X1, X2, X3, everything plus B1. When I say B1, B1 is not just only one. It is the bias of this one, bias of this, this, and this. Is this okay? So this is nothing but Z, which goes into this particular part. So Z means only this entire component is Z1 only here. And when I say Z means all these things, all the vectors, which is goes inside it. So having said that, now if any doubt is there, clarify now before things becomes messed up. So let me clearly say once more so that we are on the same page. We want to understand why can't we use a linear function as a activation function? Why only no linear function are used as a activation function? Now to understand this, I have taken a simple two-layer structure. There are three inputs and four neurons in the hidden layer, one neuron in the output layer. And we are seeing this entire set of weights corresponding to this particular layer, that is a first layer in the input layer. Let me denote it by capital W superscript 1. Superscript 1 means it's indicating that it is the weight corresponding to this first layer, likewise second layer, right? And these all are the output of the activation function corresponding to layer this one. Similarly for this, and based on this I have told you how to write all these things. Now once you have this, and when I go for a deeper structure, so which we say here as a this one W3 A1 etc. If that is the case, so if I want to write like this, can we generalize further? Can we write a deeper network something like this if it is multi-layer? So how do I go about this? This we have already seen that, okay, this is the case how it can be only two-layer structure. What about the deeper structure? So deeper structure means 1A. This is the outcome of the first layer, which I am saying that phi, and here we have W1 X plus bias corresponding to this layer. Remember. Now imagine that here between first layer and the output layer, there are many layers in between. There are many layers, and we are going to generalize. Let's say there is another layer, and I'm saying what is the output of that. Output of that will be phi W2. Now here it is not the X. Remember that here X will not be there, but this as a input will be available for the next layer. So this is nothing but this entire part will be available here as an input, that is A1 plus B2. If that is the case, I can keep on going. Let's say suppose some R minus 1 layer I'm talking about. So phi W, remember that whatever the index is there, you are talking about layer, the weights corresponding to the same layer are used, that is R minus 1, and to this the input from the previous layer is taken, so that is A, and here R minus 2 plus B R minus R-1 from the same layer, right? Now likewise, and if it is there, and let's say my output is the final layer, that is HX, I'm saying. So this I can write it, and I'm saying that output layer most of the time it is the linear activation function, means we don't use any phi over here apart from the linear. So whatever is there that will appear. So that will be, that is the rth layer. So WR A corresponding to the previous layer plus BR. So this is how a deep learning architecture, fully connected architecture, is analyzed. So this will give us some rough idea, right? Now we'll return to the question that why can't we use a linear function? So let's take a simple thing, and we are saying when I say linear function means if phi of z is there, output should be z only. So let me say a simple new network which we have considered. So Hx we are saying as a W2 and A1. In this case, let's ignore the bias. Let's ignore the bias for the timing just to get an understanding. if WT A1 is there something like this, so W2 let it be, you know that A1 is nothing but this, right? But you are not using any activation function other than the linear. So this will not be there. So instead of A1, I'll write this entire part. Okay. And I'm ignoring the bias, so I can just write W1, W1X, which I can say, suppose, say W prime X. Now this will give you sufficient stuff for you to understand what is happening. What is happening in this equation? If you see that, is basically we applied everywhere, we are applying linear function to another linear function. When you apply linear function on another linear function, definitely the outcome will be linear function only, means the input multiplied by some constant factor, right? Now, so what will happen that the whatever the representational power of your neurons are there, that will be lost, because oftentimes the outputs are trying to predict, they have basically no linear relationship with the inputs, not the linear relationship. So this is the problem why we don't use a linear activation function, why we use only no linear activation function. Also, if you use this without no linear activation function, the neural network will simply perform linear regression, nothing more than that. So this should be known to you. Now tell me if there is any problem here. Please. Is there any issue here? All is clear? The question can be asked something like this, that show why a linear activation function cannot be used in a neural network system. And what will happen instead of this one you are using that activation function. So, and what is the meaning or interpretation out of it? And this is very practical kind of thing. And somebody is coding in either PyTorch, Python, or Keras, or whatever TensorFlow, and they can check how things are happening. If they use a linear activation function, then they'll completely lose the representational power which normally a nonlinear activation function has. The reason behind is whatever your supervised learning, the data you are giving it to it, you cannot say that output is linearly a linear combination of the input. So it is not always the case, right? So that's why it is very difficult, or it is not possible to use linear function to model such kind of stuff. Now let me go back to today's proceedings. So today we'll start with another process or module within this, of course, chapter only, something called learning process. So the primary property of neural networks is nothing but learn from its environment and improve its performance through learning. Can anyone of you tell me what do you mean by environment here? Please, bolo bhai. Can anyone of you tell me what do you mean by environment here?
The training set?
Training set, yes. Because actually I should say it is the scenario, problem scenario, which is nothing but available in terms of the training examples. So that is the environment. Okay, good. And when you say improve its performance through learning, so what do you mean by this here? Improve performance through learning?
Real world implementation, like we launch it to real world for it to improve.
No. So what happens means when I say here, so already you have a training data available with you. And let's say some thousands of examples are there. So initially you did on the first example, you trained something and you found error is more, and that error is propagated back, changes happen. Okay. And then you take another example, things happen changing, maybe error is same, and you keep on training. So what is happening that whatever the mistake it is doing, and somebody is giving feedback, no, you should not do this way. this is the right way, and based on that feedback you keep on improving. This is what I mean by improvement by through improving performance through learning. And this will talk about something, a beautiful algo which was given by Joffrey and other way back in early 80s, I think. That is called backpropagation algorithm, and we'll see how it happens. Okay. Oh, and then iterative adjustment of the synaptic weights because of this learning. So learning reflects in the adjusting the weights. How do I know that it is? Basically, the weights keeps on changing. Otherwise, no learning will happen. Now, definition of learning due to this two people, Mandel and McLaren, basically, and they talk about something like this. So let's see this. They say learning is a process by which the free parameter of a neural network are adapted through a process of stimulating by the environment in which the network is embedded. Now, before I proceed further, first a few key terms are there here. Free parameters. What do you mean by free parameters? Anyone of you? What do you mean by free parameters?
The weights.
So in a simple language, free parameters are nothing but the variables. Okay, variables will be keep on changing, or simple to say that variables. So in this case, two variables are there, free parameters, which can be considered weights and the bias. Okay, so say that learning the process by which the free parameters of a neural network, that is the weights and bias, are adapted, means getting changed through a process of stimulation by stimulating by the environment in which the network is embedded. What do you mean by the process of stimulation or stimulating? Why I'm emphasizing it, that you should really perceive it. What do you mean by? I'm not looking for a conceptual you read and vomit it on the paper. No, no, no. Try to understand. What do you mean by stimulating? Network gets stimulated by the environment in which it is embedded. How it will be get stimulated?
The neurons will fire, sir, or the
How?
units will be firing based on the weights and the input and also the activation function.
Okay. See, so here it says that process of stimulating means things will keep changing by the environment, which is nothing but it is emulated by the training example itself. And it says that in the environment in which the network is embedded, ultimately to say that the network, what kind of data, training data you are subjecting to. So it will get embedded into for that particular environment. This is what I mean to say. Now, type of learning is determined by the manner in which the parameter change takes place. So basically, there are so many learning algorithms. So why not only one? So basically, that's what is mentioned. Says that what kind of learning is happening. So, for example, like we all human beings, as we say, we are basically master neural systems we have. Do we learn in, or do we all learn in the same way? Hello? Do we all learn in the same way with the same pace and speed?
No, sir.
No. Each one of have our own way of learning something, and some are fast learners, some are quick, some are slow, some are moderate. So likewise means how those learning happens or how the parameters are changing, accordingly different learning algorithms are there as well. So there are some few basic learning process which is this one Hagen has removed it, so even I have updated this particular part. So those are classical in nature, but they are beautiful, but we'll not discuss about that. I will see how the process going on. Then this learning, when we say learning, so sequence of events in a neural network learning are few. The first of all is the neural network is stimulated by the environment, means you give the input to the neural system and those values are started being calculated. And as somebody says, neuron getting fired, okay. And so neural network undergoes changes in its free parameter as the result of this stimulation. So I want to tell you now that during this particular process, what happens, there is something called forward pass and backward pass. So those things we'll discuss after a few more lectures. So initially what will happen that during forward pass means when the example is given to the neural network and the all activation potentials are getting calculated. So there is no changes in the free parameters happens. No, whatever the initial values are there, based on that calculation will happen and the value will be coming. So for example, I'll just quickly tell it in reference to the network which we have taken. In this, suppose you have taken one particular instance of this, but before this instance, network has to be initialized some value. Means some bias will be initially, some bias will be there, and you may randomly pick some weights value. Okay. Sorry. And then you give this input. So accordingly, this will be calculated and this will be calculated accordingly from this, and this weights will be there. This will be calculated. Now what has happened? This is the output corresponding to this kind of input which you have calculated. But in a supervised learning process, what has happened that this output which was produced has to be compared with the actual or the desired output available corresponding to this one. And the difference between the two will be propagated back. So remember that this, whatever just actual output you got now, is something called forward pass. During this, no parameter changes happens. Remember that no parameter get changes. We calculate this hx based on the whatever the value we have taken it. But once we get this, we compare this hx, that the actual output produced by the desired output, and the difference what we get error, we propagate back. While propagating back, in due course of process, this bias changes, this weight changes, this weight changes, and finally this bias also changes. So the statement which I gave here, the neural network undergoes change in free parameters as a result of this stimulation. So this happens in the backward pass. Also, neural network responds in a new way to the environment because of the changes that have occurred in its internal structure. When I say internal structure, what do you mean by that? What do I mean by that? When we see internal structure?
So like changing the hidden layer, number of neurons in the hidden layer, or
No. That's what I wanted to clarify so that you should not get confused. So let me go back here. So I said that you have taken one particular problem scenario here. Let's say a very simple scenario. Let me say this is my x vector, which is something like this. 1 0 1 0 0 1 1 1 1. Let's say simple. And corresponding to this, there is a desired vector variable is there 1 0 1. Let's say. So this is my first instant x1, x2, x3. When I give this, and these are the some initial weights and bias, and based on that I got the values, let's say 1.4, right? But you know that corresponding to this example, as per the training data, the value should be 1. So you find the error, that is the hx error minus whatever this y1 is there, whatever this value comes out to be 0.4, whatever, this has to propagate back. This propagation that I'll talk about later, which results in change in these weights. So this changes will happen, and this finally when I propagate back, this changes happens. When I say we reflect something, this changes happen. Now this kind of changes in the synaptic weights and bias are called a change in internal structure. So this is what I mean to say internal structure. I'm not saying change the architecture. Remember this word, change in internal structure. So that's why I'm emphasizing a lot on this. You are stimulating, you are calculating the value of hx, etc. After back propagation, you are changing the free parameters. Now, due to this change in free parameter, now your neural network responds in a new way to the environment because of the changes that have occurred in its internal structure. What I mean to say, when you back propagated this, so this all synaptic weights have changed. Now you apply second set of example 0 0 1 and then 0. So when you do this, a different value will come. Now it is completely work in a different way, and accordingly forward backward pass, it will keep on happening. This I what I mean to say. This will be more familiar when we do with this uh, when we talk about MLP. So just hold on till that time. At least I wanted you to have an idea, and it should not be superficial idea. You should have very concrete, oh man, this is how it works. So I'm looking for that kind of understanding, not a shallow understanding. Now, once we have this, so at a prescribed set of well-defined rules for solution of the learning problem is called learning algorithm. Means how your learning synaptic weight should change in response to the what should say error you're propagating. So that is a predefined, well-defined rules, and those rules we'll see some of them. This entire, so basically entire part is your segments are majorly we are talking about the supervised learning, and some part will be semi-supervised. This one unsupervised learning in one particular instance will be clustering. We'll see that. So also the manner in which a neural network relates to the environment dictates the learning paradigm that refers to a model of the environment operated by the neural network. So here point to be noted, the manner in which the neural network relates to the environment dictates the learning paradigm. Means that how it is responding and learning from the environment, it's a completely different way of learning. So likewise, there are basically learning paradigms, but before this learning paradigms, so there is something called credit assignment problem, and then there is broadly called learning with a teacher and learning without a teacher. So learning with a teacher is also known as a supervised learning. Learning without a teacher is called a unsupervised learning. But before that, a related term, what is called credit assignment problem. So what this credit assignment problem is, that something like this. The question is how to assign credit or blame for overall outcome to each of the internal decision made by learning machine. So this kind of things we say credit assignment problem. Means how the outcome is there, whether it's right or wrong. If it is right, so what should be the credit given to the system? Means is there any way to reward it? Or if something goes wrong, how to blame. When I say blame, means whether the weight should be punished or which one, means some sort of a rewarding function will reflect in some sort of punishment. So basically this kind of things happens oftenly in reference to reinforcement learning, that we'll see. But also in many cases the outcome depends on a sequence of actions, not one. So assignment of credits for outcomes of action. Remember, assignment of credit for outcomes of action, that is temporal credit assignment problem. That is, when does a particular action deserve a credit? Also, there is assignment of credit for action to internal decision, that is a structural credit assignment problem. Assign credit to internal structure of actions generated by the system. So these things happens quite oftenly in terms of reinforcement learning. So also this credit assignment problem routinely arises this in neural network, and simply to say that which neuron, which connection to credit or blame. When I say credit or blame, is there any way to reward, use some sort of rewarding function or punishing function? Basically reward function, when you say the value change accordingly, credit or blame happen. Then we'll move slightly to this, and which is more part of interesting for us, part of interest to us, that is learning with the teacher, which is oftenly called as a supervised learning. Supervised learning because we have the environment, means entire training data is available with us. So these are the environment, means the input attributes, and when I say teacher, you can say nothing but the label of that data, that is the teacher. Means if this is the input given, this is the output is expected. So if that is the case, this is called, you can say that is the teacher. Basically input output map is things is already available with you. Now here is your system. This kind of direction to indicate that it is susceptible to change. Change means it is learning. It's basically synaptic weights are keep on changing. Now same input is given to the learning network with some initial setup, whatever it may be. Whatever the output you get, in the example I was talking about h of x, right? That value is compared with the actual desired value corresponding to the input. And here, when I say this, so this difference is propagated back as an error signal. Error signal is given back to the system, and accordingly this will learn. Now how it is happening? So I told you that on very first or second class I was talking about. Let's say you were in the nursery once upon a time, right? And your teacher asks you to make for A or write A for apple, or you can say draw A for apple. You use the entire page to draw A for apple. Then probably she did some hand holding or otherwise also. She said, no, beta, you should not draw something like this. Only it should be in the first 4 color lines only these 4 lines. And then, so actually who does it? You're asked to do something, and but there is somebody who knows that what is the right value for this. They gave you the feedback, you learned this by error, and now instead of drawing by half full page, you did half page, so it is much better performance compared to previously. Now she said, no, this is not correct. You should go only with this 4 lines. You, after multiple iteration, you started doing this, right? So means whatever she is saying, effectively this error is, this is the error signal given back to you, means you're informed to you how it should be done, and then you start doing it. Once this is happening, remember the ideal condition that when error is 0, you are detached to the system, but it doesn't happen. You will never get a zero error system. But within this error is acceptable, then you say, okay, let's move. So what I'm trying to say that you can say here, your teacher will keep on teaching you till from the entire one page A for apple, you come to this 4 line. But in spite of her best efforts, you are still exceeding a little, a few millimeters, the 4 lines as well. But now you see, realize that your teacher realized that, okay, this is acceptable. Now there's no fun in keep on training same thing. Let's move to the another letter B and see this is how it moves. So that the teacher itself detach from this particular learning process initially for the learning A and move to another one. In the same way, this can happen. So this, as I mentioned, supervised learning. Teacher has a knowledge. So teacher has a knowledge. This how it is get emulated in system is nothing but a desired output and represented as an input output examples. Environment is unknown to the neural network. We don't know from which particular. So effectively, environment is nothing but it is simulated by the training examples you have. Also, neural network tries to emulate the teacher gradually. This is what is happens. Emulate the teacher gradually literally means that it has learned so that this input output formation happens. It learns the internal structure. So when the future you ask to for this input, what is the output? So you don't need any other output comparison. It produces the exactly. So this is what happens. So also error correction learning is one way to achieve this, but there are many ways. Error performance surface or error surface is there. We'll talk about later. Now, when we use this, so there is a simple thing to remember in mind. How do I know when should I go for supervised learning? So this to be used when scenario is something like this. I know how to classify this data or design a regression for this. I just need you, that is the algorithm, to do it for me. So if this is the scenario, you go something like a supervised learning approach. Okay. When you say I know, so what do you mean by this I know? Hello, anyone of you?
So the data set is labeled.
Yes, perfectly. Data set is labeled for this attributes. This is the expected outcome. This is what I mean to say I know. Okay. And then you say that I just need you to do it. Means if this input I give, you should keep on finding the label or the output of value depending on the problem at hand. Okay, good. Now, basically, two types of supervised learning algorithm comes, or the two flavors of supervised learning. First one is each training case consists of input vector X and a target output D, or a target output sometimes in Hagen's book he talks about desired output D. So don't get confused. So we have this. So there is and the first one is called regression problem. When I say regression problem, so in regression problem, once you have these values, you are able to find some continuous value or real values in response to that. And this is what I mean to say regression problem. For example, do you remember that I quoted one example that you have to design a rent prediction system in Manipal for the students. So you have these 4-5 attributes: number of bedroom, number of washroom, walking distance, parking is available or not, garden is there or not. You just give this input and it should tell me the rent. Now, whether the rent prediction is a regression problem or classification problem. Hello? Any idea?
So regression.
Regression. So ultimately you want to find some certain value. The label is not known a priori. If labels are known a priori, for example, if there is a conveyor belt and you have a large orchard and your people are plucking mango, apple, etc., and putting in the conveyor belt, let the system segregate into the different bins. This mango, apple, oranges, etc. So these things are examples of classification problem, not the regression problem, because labels are known a priori. Means this is a bin corresponding to apple, this is a bin corresponding to mango and guava, whatever it may be, right? But when I say through rent, the values may change. There cannot be any prior label. So now you understand the difference between the two. Okay, good. So for example, the stock of the price of the stock in a month time, temperature by tomorrow evening or whatever, and then number of COVID cases in another 3 months, what will happen, other 1 month, what will happen. These are all example of regression. We cannot think as a classification problem. Classification problem, I told you, some priorly label is there, so whatever input comes, accordingly it should be labeled that way. The simplest case is choice between 1 and 0. Multiple alternative label is also possible. Okay, so this was regarding this learning with the teacher or supervised learning. Now let's move on another one, something what we call as a learning without a teacher. Basically this also comes in two flavor. One is unsupervised learning, but another one is reinforcement learning. So reinforcement learning is something we have to discuss about little here. So here if you see the structure, it is something like here you see somebody as a critique. So this guy critique is a system basically which keeps on telling this, and a reinforcement first of all, when should you go for reinforcement learning? Remember that a scenario when you have millions of parameters to be learned or trained or hundreds of parameters to be learned, etc. This kind of things cannot be done or achieved using reinforcement learning. The number of free parameters which has to be learned is less, significantly less, few 10, 12, 15. Then reinforcement learning is a better method. Also, for what kind of scenario, let's say that a very simple thing is that you are designing a robot or say a walking robot or something like this. So there is no way to say that means how do you train this robot for walking, etc. So you design a system in such a way that you say that if I press move forward, if it is moving forward, then you give a credit for the system, means some sort of a rewarding functioning. So it's moves. But when you press forward, it's lean down to lean towards any side or fall back, then you give it some sort of punishment. So rewarding function value will go negative or something. Accordingly, these things are happening. So who does this? This is done by critique. So is the environment, and basically what happens that it continuously interact with the environment. So this was I mentioned this. So learning input output mapping through continued interaction with the environment. So it input output, if this is happens, what is the expected output and what is happening? So it continuously keeps on interacting with the environment. When I say interacting with the environment, so there's a after this critic keeps on sending the signal, and this learning system takes into account and accordingly given feedback to the system. And then we have something called active critique. So critique converts primary reinforcement signal. This is your primary reinforcement signal that you're taking from the environment into a high quality heuristic reinforcement signal. When I say heuristic information signal, somehow you tell where all this your rewarding function, etc. take into account. And you tell that whether should be punished or should be credit in all these cases. And goal is to optimize the cumulative cost of the action. So means what way we can say this, whatever the action is taken, most of the time it is a sequence of action, not one. So we'll see. So this is a very simple thing. We can say that when to use it. To be used when you say that I have no idea how to classify this data. Can you classify this data? And I will give reward if it is correct, and I will punish you if it is not. So if some kind of scenario, so that's why I give this in purple color here, it gives us some scenario, means under what condition I can apply for this kind of thing. First one, that there it cannot be used for learning millions of variables, just like supervised learning you do. But under what particular situation? Then you say, I don't know how to do it. But if you do it rightly, then I'll reward you. If you do it badly, I'll punish you. That's all. If this kind of scenario is there, you can think of a suitable reinforcement learning model accordingly. Of course, in this course, we'll not be dealing much with this because reinforcement learning itself is a one semester course. It's quite vast. And its approach is completely different from the conventional supervised and unsupervised learning. Basically, a lot of Markov decision process and Markov chains, etc. We talk about that. But I just included here so that you'll get an idea, a fair idea, what do you mean by this and for what particular scenario it is most suitable. So also the reinforcement learning, what happens, the output is an action or sequence of actions, not only one. And the only supervisory signal is an occasional scalar reward. The goal in selecting each action is to maximize the expected sum of the future rewards. This is what we're looking for. We usually use a discount factor for delayed rewards so that we don't have to look too far into the future. What I mean to say that if reward is there, if I'm getting if the rewards are coming late, so for that we don't give some value, or that means if I'm putting a seed now and after a long time the outcome comes, I'm not looking for such kind of rewards. So those things are rewarded which gets an immediate value, and this is how we progress. But remember, this reinforcement learning is difficult from many factors. The rewards are typically delayed, so it's hard to know where we went wrong or right. Okay. Scalar reward does not supply much information because scalar is one value. So if vector things happens, that is good, but that may not be the case in always. Okay. Now, in the same category, that is learning without a teacher, there is a traditional way of and what we call unsupervised learning. So here you have environment and your learning system, and its vector describing the state of the environment. That's all. So learn based on task independent measure of the quality of representation. It happens. We'll see in this. Internal representation for encoding feature of the input space. You try to find it out what is happening. When you see unsupervised learning, so you remember that the scenario is somewhat different, that here your training example will not have any label, whether it is a categorical or like from regression perspective, no values is going to be given to you. Only this, the input attributes. So competing learning rule need something winner takes all. So there is no concept of consolation prizes to others. If somebody is winner, he takes everything. So this kind of algorithms or the learning approach is used. When you say this, I have no idea how to classify this data. Can you create a classifier for me? So this kind of, and most of this unsupervised learning are basically not for the regression, mostly for the classification. So you know that clustering, etc., is one of them, the most widely known example of this unsupervised scenario. Now, so you'll be surprised that nowadays we are reading all these things, unsupervised learning and all these things. For many years, more than 40 to 50 years, unsupervised learning was largely ignored by the machine learning community, largely ignored. Some widely used definitions of machine learning actually excluded it. So they did not mention at all that unsupervised learning is there. And many researchers thought that clustering was the only form of unsupervised learning, but we know that it is not true anymore. It is hard to say what the aim of unsupervised learning is, right? Because there are many things we can talk about. One major aim is to create an internal representation of the input that is useful for subsequent supervised or reinforcement learning. So what happens that suppose the entire data is there and it's very complicated or things but it is not known to us. So we find a very quick on some sort of internal structure. So we pass through some unsupervised learning algorithm. It will go for some sort of internal representation, then later we can apply supervised. So this part we'll see in today's class only. Just hold on for some more time. And other goals of unsupervised learning can be like it provides a compact, low dimensional representation of the input. When I see low dimensional representation of the input, what I literally mean to say, for example, image is an example of high dimensional data because there are thousands of pixels are there or millions of pixels are there, right? But when this so many pixels are there, whether all pixels are playing a role in certain fact? No. So very few will be there, which are the key contributors to that particular image, and those are the basically a low dimensional representation of those particular for the entire image. This is what I mean to say. So low dimensional representation. So high dimensional inputs typically live or near a low dimensional manifolds. This is what I mean to say. So let's say 1000 dimensional picture is that pixels are there. So few 10, 20 or 100, let's say, are the key pixels, which are the key contributing factors. Also, the PCA you know very well. The principal component analysis basically is used widely method for the finding a low dimensional representation. When you say low dimensional representation, literally you mean to say that doesn't mean that you are discarding simply blindly. No, you are finding what is causing this particular attribute to behave the way it is behaving. Whether alls are playing a same role may not be. What are the key components which are playing a significant role? If you are able to find that, you need not to bother about others. This is what you mean to say this low dimensional representation. Also, it provides an economical high dimensional representation of the inputs in terms of learned feature. When I say economical means high dimensional means, let's say some 1000 dimensions are there. If 1000 dimension data can be represented, say as a few 10, 20, 15, what's a big deal? Why to consider such an entire big set of this 100,000 dimension? Why not only this? So this is what I mean say economical. So binary features are economical if you're able to represent in zeros and ones. So are the real values features that are nearly all zero if you are able to find out all are. So if you're able to convert in some sort of sparse, it finds sensible clusters in the input. So clustering etc. is there. So you want to know that what are the set of clusters available. So this kind of scenario. So these are another few goals for this unsupervised learning. Now, lastly, we'll talk few things about here, what is called learning task. So this is for the sake of completion I'm doing, but this is very, you can say that elementary or naive to talk about here, but this we do oftenly. This pattern association we do a lot. For example, this example which I'm quoting, you can relate with a pattern association or a pattern recognition, or you can say function approximation. So basically you can, this pattern association and recognition, there is some sort of similarity. So what is happening that, let's say you watch a movie today, and after watching this movie, you realize, oh man, this movie is similar to that English movie I saw. And later you realize, because the entire plot is similar, then you realize, oh, this is the same thing. So effectively what is happening, you are doing some sort of pattern association with that, or with a similar scenario, you are finding something else. The way back around 2005 or 6, I saw a movie in Tamil called Sanjay Ramasamy. And that movie, yes, the name of the movie was Sanjay Ramasamy. And I do understand Tamil. So after watching that, after many years, when I saw this movie called Ghazni, then I realized this Ghazni is nothing but is a remake of that movie completely, because you are something in the back of your mind, that particular plot is available. And when you see something, then you start relating, this is the character behaving that way. And you say, I've seen something like this. So you are associating this kind of pattern. So this is what I mean to say. So this thing in a system, how to do it, and basically how it is done from a neural perspective, let's see this. So pattern of association, when I say there is something called pattern associator. So you have input vector and there is output vector. So this memory, they say this associative memory is like a brain-like distributed memory that learns association, means this has to be associated with what. So pattern association, so there are two terms will be used, something called key patterns and another is called memorized pattern. So this xk will be calling as a key pattern and y's will be memorized pattern. So basically what happens, the sequence of this will be given to the system or exposed to the system, and that yk is nothing but we say that it is stored in the system or what we call as a memorized system. I'll do some problem based on this. So pattern association is basically of two flavor, vanilla and blackcurrant, not exactly this way. What I mean to say, auto association, that is xk equal to yk, means memorized pattern is exactly the same whatever the input pattern happens. So this is called auto association. So given the partial or corrupted version of the stored pattern, we retrieve the original signal, right? The example which I showed that, okay, I saw one movie and I say, so you say partial or corrupted version. Here I say corrupted version. You saw similar. Many movies you say that this idea is not completely 100%, but some part of this is very much similar to it, right? So this is, and based on that you say, this is how it's going to be. Because I don't remember now what particular movie is there. There was a movie like there's Ajay Devgan or somebody was there, and this was regarding a political plot in the system. And when you correlate with that, then you say, it is something like Mahabharata stories trying to put it across here. Who is a Karna, who is Arjuna, line kind of. So it is not exactly even a partial version you see. Based on that, you are able to retrieve the original signal. So it means what is the actual story. One is something called heteroassociation. So in heteroassociation, basically you cannot say that it basically learns arbitrary pattern pairs and retrieve them. So this is heteroassociation. These two things I'll talk about by a particular neural network system, which we call as a Hebbian synapse, basically Hebbian learning technique, which was of course is not part of this third edition of Simon Hagen, but I'll use that to understand. And then, so let me quickly complete this, then I'll come to the example with the board. And but here, what is the relevant issue is that storage capacity versus accuracy. Means how many patterns can be stored, and also you have to look for that what is the accuracy with which it can retrieve those values. Then there is something called pattern recognition. So pattern recognition is basically mostly in case of is statistical in nature. So there are two approaches for this, what they do it now. Instead of applying directly, they first, if you remember, I was talking about this unsupervised learning people, they apply first to find the internal structure of that, and then they apply supervised learning or reinforcement learning. So one scenario is similar to that. You give the input pattern and you don't know how it is happening or what is happening. So you try to apply some sort of unsupervised learning over it, and you did it. When you did this, you did mainly to extract some sort of feature you want to extract. Based on this feature vector, one feature vector is known to you, then you apply this supervised learning network and then you get the output. So it becomes either classification or the regression problem, whatever it may be. So this is what it says that, let's say your input was some m-dimensional observation space. When I say observation space means nothing but each example is of time dimension. Let's say the example I was talking about is rent prediction system. So dimensionality is 5. The number of bedrooms, washroom, etc. Dimensionality 5. Based on that, you apply some sort of unsupervised learning and you got a feature, means what are the key components available here. Then based on that feature, this dimensionality will be definitely, it will come down, say q dimensional feature space. It will definitely q will be much smaller than m. And then based on this, you apply supervised learning approach here, and exactly it classifies into, let's say, r dimensional, which is further lesser than q. So this is how a pattern recognition also happens. Pattern recognition also you can relate with the story I was talking about, the scenario of this movie scenario, you can correlate with that. So here mapping between input patterns and prescribed number of classes can happen. Two general types are there basically, feature extraction, that is the observation space to the feature space, and then classification, that is a feature space to the decision space. And as a single step also you can do this, observation space to decision space also possible, means only one kind of unsupervised learning you do this. And then we'll move next and something called function approximation. So effectively entire supervised machine learning or the neural network approach is nothing but an example of function approximation. When I say function approximation, what I literally mean to say that means you have this kind of system with you, and let's say this is your data set, and you have this kind of values x1, x2, let's say xm is there, and you have these values are there with you, right? Or let's say this is m, and this, say this many mn scenarios are there. So basically you can say that this is m cross n, means each training example is of each of dimensionality n cross 1, right? And the entire your matrix is, the training matrix is basically m cross n, and corresponding to this you have y, of course, that is the label set which you want, right? So you can say this is m cross 1 if it is only one. So you just wanted to know, man, whenever this x1, x2, x3 is there, this is the y value. Another scenario is there, and let me call as a first scenario. For the first example, we have this first one. Whenever this first attribute for the another example, if I take it, when I say in bracket, it doesn't mean the square, it's just to represent that it is second example. So you have this value, right? And possibility that these two are quite different. So you just wanted to know, man, can I find something like this? Which tells me that whenever this x goes, I can find this. So effectively, this is, you are trying to find this one, f. And this is exactly what you do. So this is your black box, either you can say neural network, which you don't know exactly. And so you have this kind of inputs, x1, x2, let's say xm, and you want to predict y, right? So from this training data, you want to looking for something of that sort, but you don't know what is that. So you want to approximate, you want to find that structure, and that is nothing but function approximation, right? So this is an example of function approximation. So here, this is what you are looking for. You are looking for no linear some sort of input output mapping. If linear was there, it's not a problem at all. Straight away could have been done. So for unknown f, you don't know what is that particular f. So this is, remember, so a very naive approach will be apply. So this kind of training data is there, xi and di, I go to 1 to n, means these are the set of data sets. For each xi, there's a label. I won't say label, so desired value is there. You want to estimate this f, that is a function, such that fx, so you want to estimate this, then, but this is something true value, which you don't know, which we can be represented by di, right? So you want to find the particular function fx, so that the difference between the actual calculated value and the desired value is the Euclidean norm is less than epsilon. You are looking for something. You are, when I say approximation, means definitely it will never be equal to the ideal value. So what is next near to it? And this should apply to all fx, not for only one. So this kind of scenario, what we call as a function approximation. So there is something what is called system identification. So the system identification, when I say this is nothing but your function approximation problem only. Here you have input vector, and this is unknown system, means f is there, you don't know. Only thing you know that for the set of x, this is the desired value. So corresponding to that, you give a design in neural network. You don't have what you don't know the idea about this. So some rough guess you had based on the last class we discussed about, means some idea. This is problem will give you what should be the number of neuron, etc., whether it is having bias or not bias, hidden is there or not there. Based on that, let's say you did some naive architecture you drawn, and same input you started giving, and based on that it started producing one value, and you are comparing the two. The array is there, you keep on changing this, keep on changing, and this learning process keeps on happening till when you will detach this part, when you feel that, oh, you're able to do fairly well. So it means that this, whatever the function you have found or the network you have found, is representing the exactly or mimicking the behavior of this particular function. So this is what is called system identification or function approximation. Another is inverse system modeling. When I say is inverse system modeling, so problem is slightly different. In this case, you want to find it this way such that for that particular desired output, what should be the attribute, right? So what I mean to say, for example, this the rent prediction system I talked about. Okay, so rent prediction system which I was talking about, let's say a scenario that uh, your budget is say some 10,000 a month. So you want to know that your approach is completely different now. Earlier, what you used to do, you used to enter the specification according to you. Okay, 3 bedroom through 3 washroom, etc., etc., garden, walking distance, and then it predicts the value. You want to say that like this much money I have, 10,000. With this much 10,000 rupees, if I put in a system, it should tell me that specification for all those attributes, means how many bedroom I can get, how many washrooms will be available, whether garden is there or not, walking distance, etc. If such kind of scenario is there, so this is a problem can be found, a system can be trained, and what is called inverse learning inverse function. When I say learning, please note that this is not the mathematical inverse of this particular function, nothing to do with this. So be very careful about it. So this is what is having. So you have this input vector. Already you don't know what is the function is all about, how it is working. System output is there, and you have inverse model. When I say inverse model here, for sake of writing, I've written inverse model, but effectively some sort of neural network architecture is only working, right? Now for this, remember that earlier we were comparing with the output. Your intention is not the output. Now system is that inverse modeling is happening. From this you will be producing y. Y is nothing but some sort of x only. You are looking for the inverse problem, the attribute set. And this attribute set you compare with the training data attribute set. And comparing, and whatever the difference is there, you keep on giving to the system. And this process will keep on happening till when you will detach it, you will find that this error is negligible or acceptable. At that moment, you will remove everything and you know that the system is there in place. Okay, this is the desired output. If I give, the system will give me this many the attributes with their respective values. So this kind of problem is called this particular problem is called inverse system modeling. So I stop on this particular part. And a last part of this is that there are, if you ever come across this MATLAB, so there are multiple functions into it. So I don't know what's the command or code for them in the TensorFlow or PyTorch, but similar things you can see that. Hard limit is nothing but this. These are different types of activation function used. Hard limit is nothing but the thresholding function. Basically, whenever the value is greater than 0, it is 1. Otherwise, it's less than 0 means 0. Symmetrical hard limit. When I say symmetrical hard limit means -1 and +1. Linear, you know, is basically whatever input is same output. Saturation, so you set linear, etc. Similarly, you have log sigmoid, tangent function, positive linear, competitive, etc. So before we move next, let me take a 5 minutes time and quickly give an example in another 5-7 minutes of the pattern association I was talking about. Otherwise, you'll see that, oh man, this guy was telling I'll show, but he missed it. No. So let me show some pattern here. So let me say some pattern here. So 1, 2, 3. And just to show that, let me color it here with the one particular thing, and just hatching I'm using. Another pattern is there, input pattern is there. I can have something of that sort, and maybe a different way of things working. Okay, let me call this as a key vector x1. This is key vector x2, right? So, and the notations which we are using, wherever this hatch area is there, we are going to represent by +1, let's say, and unhatch area by -1. But nobody can stop you from reversing the two. There is no problem. Once I have this, so let me write this in terms of vectors, vector representation, which is quite easy based on the notation we follow. So we'll take it this way. We'll read vertically and then this concatenate. This is what we do this when you go for MNIST, etc. So let's take this vector. So wherever there is this 1 1 minus 1, then 1 minus 1 minus 1. So entire thing basically one part you read and then concatenate another one this way. So you have 1 1 1, sorry 1 1 and then minus 1 for this blank. Then we have 1 here, then minus 1 minus 1 minus 1 minus 1, and basically I'm writing in this one, actually it should be a column vector. I'm writing a row, so I'm writing a transpose. Another one similarly I can write like this: minus 1 1 1 minus 1 1 1 1 1 minus 1. So 1 1 is done, so another 1 1 minus 1, and this is again like this. Now the first question is for you, and you have to do it now immediately, whether these two vectors are orthogonal or not. If I directly say that, check whether the given patterns are orthogonal, may be difficult for you to realize and visualize. But when I say this, then you have a way to do it. First, convert into vectors. And when two vectors are there, how to check whether those two vectors are orthogonal or not? Anyone of you? Quickly. Please tell bhai.
So the dot product is 0.
Yes, so simple to say that dot product is 0. So we have, so on that day, that's why the basic linear algebra, whatever I reviewed. So I have x1, x2. So dot product is 0. We'll see that 1 into minus 1, we have 1 plus 1 into 1, 1 plus this minus 1, this is 1, so minus 1. Then this 1, this 1 is 1, this minus 1, this 1 is minus 1, this minus 1, this minus 1 is plus 1. So this will go, this will go 0. Yes, in this case I can say yes, it is the case. This one is orthogonal to x2. Another question comes, it says that design an auto association for these patterns and use the Hebb rule. It says that design the auto association. When I say auto association, or remember this, I talk about hetero association and auto association. So when you say auto association, whatever this vector is there, this is same as represented auto association. So there is something called Hebb rule. So I'll not go too much into detail about this. So Hebb rule, you can see that the vector, the weight matrix will be nothing but the y, this is a learned pattern, outer product with the input pattern xt, right? So with this, now before that, let me find x. What is x here? So entire x is your the key patterns x1, x2. So when I say this one, so let me write this entire x. So this is, I'm not going to write this t anymore because they are basically column vectors. So we write like this. So we'll write something of this form. So we have 1 1 minus 1 1 minus 1 minus 1, that part. This one is minus 1. So 1 1 1 1 minus 1. So this is my entire x, right? When I say you are required to find a design auto associator as per the Hebb rule, Hebb's rule. So it is something like this. It's nothing but the outer product, remember this, of y, memorized pattern, and this, the key patterns, the transpose, the outer product. Remember, when I say outer product, the overall thing is basically a matrix, not a scalar. Remember this. This I talked about earlier, inner product or outer product. When you go for this, you are required to find the auto association. Auto associator means y is nothing but the x itself. Y is nothing but the x itself. So in this case, your W will be nothing but x xt. So when you substitute this, all these things into place, when you do this, so you have something like 2 0. I'm quickly, for the sake of times casting, I'm doing this minus 2 0 minus 2 0, etc. you can fill it up, right? So you'll be able to get this kind of matrix. Now another question comes to you. So let's say this one is there with you. Another question is same if I give you and I say that now auto association is there with you, means this is the system you have designed and this is the weight matrix, you got it. Now the question comes, if I give a pattern to it, can you recognize it? What does your auto associator will give the response to me? Suppose if I have this kind of pattern. So it is something like this and this. And let's say this is my test pattern xt. What I wanted to know, your auto associator which you have this kind of weight matrix W is there. If I give this as an input, what is the output I'm expected? Which kind of pattern it is? So remember that whenever you have something like this, so what you have to do this, you have to find the output. So output, you know that as per the conventional thing, you need first activation potential. So Y is nothing but some sort of phi, and here your WXT. So this is nothing but WXT. So W will be coming from this. XT is this one. So you can find it out very clearly. What should I write here? How can I write into pattern value? What should I write? 1, 1, 1, 1, 1. Last one is -1. T. Give me just 2 minutes. I am done almost. And then you can use whatever the value, because it is using 1 and 1. It means is some sort of activation using is basically nothing but hard limb. Hard limb means this kind of value across this one. Greater than 0 is +1, less than 0 is -1. This is +1. So I can apply and whatever the value here in xt, you do this, and after doing this value, let's say the value comes, phi comes, and you have something like this. You have, let's say this value comes, I calculated -2, 6, 2, 6, 2, -2. If you have something like this, so what is the value is expected if your phi is hard limb? Any one of you quickly? Give me 2 minutes and done. -1, 1, 1, 1, and -1. So wherever value is negative, wherever value is positive is +1. That's all. It's a hard limb. Now the question comes that this particular pattern is similar to what? Whether it is similar to X1 pattern or similar to X2 pattern. How do I know this? Which one is the correct? Because this is just a response. So you have to say. So what I'm trying to say that you gave some input, you saw one particular plot, and based on that plot, basically a partial or corrupted version of any of the training part was given to system, and it has to find the original version. So which one to talk about? So there is something called, before that, there is something called Hamming distance. Before that, we use this concept and use the concept of this Hamming distance. So Hamming distance, you know that's how do we calculate? This you've done in your communication classes. So nothing but Hamming distance is basically you find a number of ones in, let's say, code 1, usually XOR with code 2. So once you have done this, you'll find. So let me quickly come to this one. And here all ones -1, yes. So I'm writing here just to sake of clarity. Or I am writing here 1, 1, 1, 1, 1, -1. Now if you take the XOR of this and this, don't worry about this transpose. Of course, this is also this one. So what will be the output? This is a 1 by 1 we do, right? 1, 1, so 0, 0, 1. Here differences are there. +0, +1, +0, right? Once you do this, find how many number of ones are there in this. So you find 2. In this xt, again you find. Now compare with xt. So 1, 1, 1, 1, 1, -1. Based on this two things, you're trying to find the Hamming distance. So let's see that. Here it is 1 0 0 0 0 0, right? All zeros. So you can say that 1. Now I can just write here Hamming distance of x1 and xt is 2 and Hamming distance of x2 and xt is 1. Now once you have this, Hamming distance is some sort of similarity measure in the pattern, you can say that. I could have not used Euclidean distance over there for similarity check, but Hamming distance. When I do this, we can say that the test pattern is more near to x2 as compared to the x1. So the pattern is similar to x2. This is the what you are expected output. Okay, so this is how systems are working, and work on that. And I'll try to give you some practical perspective based on this, and accordingly you can expect something on that. So that's all for today. So wait a minute. Sorry for taking extra 5 minutes.